angst about the homework. So I thought it'd be good to.
There's still.
There still is? Okay. I thought it would be prudent to go over and to explain A, how we're doing it, and B, why this is so important that I can't cut it out. So let's look at problem 3. Have either of you completed problem 3?
I just have one question.
So you're close to completing it. Well, so this will be more for Chad's benefit than yours.
I want to go through it. Yeah.
Okay. So we have, consider a CN, that's cyanide, is that right? That may be described by a dumbbell consisting of two masses. I was like, that's not proper English. Two masses, that's by a rigid rod of length A. I'm going to read carefully. The dumbbell rotates in a plane about an axis going through the center of mass and perpendicular to it. Assign the z direction to be the direction with zero angular momentum, so ML is 0. So the first thing is I'm going to draw a picture.
Is number 3 the one that we couldn't do?
I looked at it afterward, and it was something we could do. I was wrong in my statement that we couldn't do it yet. So here is our molecule. And since it's carbon and nitrogen is more massive than carbon, we make it like that. So, and it's a little bit bigger to indicate more mass. Although in reality, which one's bigger? Carbon. Because it's held more tightly. Or the nitrogen is held more tightly.
Yeah, as you go right, it's
Yeah, so it's smaller. At least that's my recollection. I'd have to look
But
again.
is that enough to balance out the increased size of the nucleus?
Well, the nucleus has no marked effect on the size. The charge of the nucleus has an effect. Okay, so here's our picture. And the first question is, what are our axes? It describes one axis, the z-axis. What direction should that be? Come on, Richard. Okay, at least I got it highlighted so I can stretch it apparently. Really? All I want to do is to move this. All I really wanted to do. I'm not going to move it. What direction would the z-axis be? It says the direction where it has no angular momentum. If I have a rod of 0 thickness, what axis can it rotate on to have no angular momentum? Well, that's what we're defining as the z. But yeah, if it's going like this, if it's 0 thickness, there's no angular momentum with this. But there'll be angular momentum with this, there'll be angular momentum with this. So we're defining z as the vertical direction, the way I drew it. So we have our directions here. It doesn't make a lot of difference what how we mark it, but just so we've got that down. And the problem gave us that we have masses M1, M2, and separation A. I see that every time I change color, it didn't take. So there we have our physical situation, and we're asked to do 3 things. First part, write the Hamiltonian. Write down a Hamiltonian. So what kind of energy does this have? Let's start with simple questions. Kinetic energy, does it have kinetic energy? Yes. What kind of kinetic energy? Rotational. So we're going to have kinetic energy is 1/2 I omega squared is one way of writing it. Or another way of writing it, just like with translational, we had 1/2 mv squared, or we could write p squared over 2m. We can use the relationship that L is equal to I omega to then replace omega is equal to L over I and put that in. And so this is going to be L squared over 2I. Follow? Okay, so that's our kinetic energy. What about potential energy?
Wait, I guess I don't. You were substituting in the kinetic energy for p squared over 2m.
Well, I said like that, except we're using L, where we have I instead of M and V instead of omega and L instead of P. So it was analogous to that. What about potential energy? They're fixed, so you have no spring. You have no change in any kind of electrostatic attraction if they're fixed. So we can just set that to 0 arbitrarily. And we standardly ignore gravity. So what do we have for potential energy? Nothing. So our Hamiltonian is equal to the kinetic energy operator plus the potential energy operator, which I'll go ahead and use V since that's what we've been using up to this point. So when I put that in, it's going to be angular momentum operator squared over 2I plus 0. So that's it.
You say, is that supposed to be L squared?
Yes. Right, it was squared there. Now to hit undo twice. So that's step A. That's our Hamiltonian. Now step B, I think, was to find the question, Chad?
So simply the Hamiltonian is just the total energy.
Yeah, the Hamiltonian is the total energy operator. So B, I'm going to go back and make sure I do remember. What is the energy spectrum, the possible values for the energy eigenvalue? Okay, so how do we find the eigenvalues?
Normally, we get a matrix, but we can get a matrix from that.
That is one of the methods, but it's not the method we are going to use here. We're going to use the one we did first.
So H operator acting on psi gives the eigenvalue times psi.
That's right. So you have that. And so we need to find the eigenstates of the Hamiltonian. But since the Hamiltonian is L squared, what do we call the eigenstates of the L squared operator?
Angular momentum states.
Actually, we call them the spherical harmonics. Remember, everything we've been doing, we had L squared psi equaled H bar square root of L, or no, not square root since it's L squared. We had H bar squared times L plus 1 psi, where psi had the spherical harmonics for the angular part, and then it had that Rodriguez formula for the radial part, or polynomial for the. And so since we're not dealing with the radial part, it's just the spherical harmonics, just the angular part. So I could replace this psi with the y Lm, because y is what we typically use for the spherical harmonic. So I don't have to do any work. We've already done all that work. I have to recognize that that's the That's the function that's an eigenfunction of this operator. So we have our eigenfunctions, and what are our eigenvalues? I'm going to change this from psi to y. It would be fine to leave it as psi. So if you have it as psi, don't go changing it to y to match what I did. What do I have for the eigenvalues here?
Well, it's h bar squared all times L plus 1 over 2y.
Now, since L is the quantum number in there, I'm going to put a subscript L. That's my energy spectra. Or spectrum. It's my spectrum. Because L equals 0, 1, 2, dot, 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 dot. Those are the possible states. And then we have part C. We are so close to done. Part C says, find the difference between the ground state and the first excited state. So what do I need to know that I don't already know? I. Now, I is about an axis, and that axis is the line going through the center of mass. So I'm going to have to do a little work here. I talked about, I think when we briefly discussed it, it's going to orbit about its center of mass. And so how do I find that center of mass? I suppose those words actually work. What we do is we first do x center mass equals, and I'm going to just say x equals 0 at M2. And so it's going to be x1 M1 plus x2 M2 all over M1 plus M2. That's the simple center mass equation. That goes back to first semester college physics. What? It's a poltergeist. Just your standard poltergeist. We'll call the Ghostbusters. So x2 I said was 0 just for my reference. And x1 then is going to be a, right? If this is at 0, then x1 is equal to a. So I have a m1 over m1 plus m2. That's as far as I can go. We don't have what m1 and m2 are. Now I could look up what the masses for carbon and nitrogen are, but we'll just go with this. So then we have R1 is equal to, oh, look at that. I did such a bad job of numbering. I had R1 going to M2 and R2 going to M1. That would be kind of poor numbering. So R1 is equal to A minus X center mass, and R2 is equal to X center mass. That is, if we look here, we have the equation that X2 is equal to X center of mass, because that's the distance from the center of mass to item 2. And then R1 plus R2 equals, that's nice work, Richard. R1 plus R2 equals A. And so then that gives us R1 is equal to A minus R2, or A minus X7. So putting in our equation, there's our two radii. Now that we have those, the center of mass is sum of I be m1 times a m2 over m1 plus m2 quantity squared plus m2 times a m1 over m1 plus m2 quantity squared. Hi, Nate. Follow? So now we can simplify this. Notice I'm going to have an a squared in all my terms. I'm going to have an m1 and an m2 in all the terms. Then I'm going to have, right, so the first one is m1 times m2 squared, so it has an m2 remaining. Second one has an m1 remaining. And all of them had m1 plus m2 squared. Well, I can cancel this m1 plus m2 with one of those. And I'm left with I is equal to a squared times m1, m2 over m1 plus m2. Now, something, right, you're writing a paper about the perturbations. And here is one of the perturbations. This thing right here is called the reduced mass. Because the electron is orbiting the center of mass, it turns out that with all of our work with the hydrogen atom, if we replace the mass of the electron with the reduced mass between the electron and the proton, then it takes away that error. So that's one of your corrections that can be trivially replaced. You just replace the mass of the electron with the reduced mass between the electron and the nucleus. Now, if we do that for the hydrogen atom, mu is what we use for it, the Greek m. Mass of an electron times mass of a proton over mass of electron plus mass of a proton. How's the mass of an electron compare to the mass of a proton? Really small. So the denominator is roughly equal to mass of a proton. And so you can roughly cancel the mass of proton with the denominator and you have mass of electron. That's why it was very, very close. But if you want to be precise, which is what we want in our chemistry, then we use the reduced mass and it shifts it just a little bit more correct. Okay, so we found the moment of inertia. So now we can actually find values. So we have energy 0 equals h bar squared times 0 plus 1 over 2 a squared m1 m2 m1 plus m2. That's my energy 0. I wrote it all out, not because I'm an idiot, but just because I want to make sure we realize what we're doing. What is that equal to? Energy 1 equals notice now I will have, this is 2 that cancels with that 2. And of course, the 1 doesn't matter to us. So that's going to be h bar squared times m1 plus m2 over m1, m2. A squared. Thank you. So that is energy one. So the difference between the two is just that. Now, let me go back and make sure I didn't miss something in the write down expression for the difference in energy between the ground state and the first excited state in terms of the masses in A. So there you have it. There you have it.
How would you find the A value, the molecular diameter?
Not molecular. Well, okay, yeah, I guess it is. I thought you said atomic, and I was like, no, not that. So how would I find that?
Because Dr. Osborne told us a way to find it using classical physics, or like the way that you use it with viscosity measurements. But how does quantum mechanics deal with quantum?
The actual way you would do it would be to calculate the molecular orbital, right? Instead of atomic orbital, molecular orbitals, and then find the dE dr set it equal to 0. Where that's 0, that's going to be its equilibrium length. Don't think I've ever done that. I might have a long time ago.
Yeah, because you have to find a cutoff, right? Like you have to find a probability density that like matches the interval you want, and then because there's not actually like a specific set diameter between them. There's always going to be probability of finding one.
Yeah. And in fact, it's not rigid, right?
Right. Yeah.
But that was another reason why I wanted to go through this homework. Is this applicable to chemistry? It absolutely is. When you look at the spectra from molecules, you have you use like your FTIR spectrometry, right? Fourier transform infrared spectrometry is what it stands for. And what you see then is I have this frequency and this frequency and this frequency and this frequency. You guys familiar with those and reading them? What information do you get from those?
Well, it's IR spectra.
Yeah.
You can get the functional groups from those pretty easily.
How?
From looking at their vibrational energies.
Okay, from looking at their vibrational energies. Now you have two things, and both of them appear in the FTIR, well, the IR spectroscopy. Right? FTIR is the type of IR, so I don't need to say that. You have one is this, the rotational. So if you have something that is like this, a diatomic molecule, it has simple rotational energy states. And so you can have no energy in it, or L equals 1, L equals 2, L equals 3, and so on. So you have those rotational energy states available. You also then have the vibrational. Remember, way back when we did the quantum harmonic oscillator, that quantum harmonic oscillator is absolutely applicable to chemistry because the bond between the C and N is not fixed, as you were saying. And so if it has any temperature above absolute 0, you expect it to do a little oscillation, except for quantum mechanics. What did we find when we were doing the quantum harmonic oscillator?
Did we do that in class, or was it homework?
Yeah, we did it in class a long time ago. It was the second problem we did. Or maybe the third, maybe we did finite box before we did it. Remember, we had the two ways of doing it. We found that it had quantized energies that were, so this is vibrational up above this line. Or not vibrational, this is rotational up here. But for vibrational, we have the energy is equal to h bar omega times 1/2 plus, and I don't want to use n because that's our principal quantum number for an atom. So I will use Okay, epsilon, sure. Where epsilon is the positive integer. So it always has to have some vibrational energy. It can't be a fixed dumbbell, apparently. It's going to have some vibration. And as the temperature, at low temperatures, you actually don't have enough energy to make it vibrate. You get up to higher temperatures and you can start the rotation and you can start the vibrational modes. So it basically, if I understand correctly, it behaves like a fixed bar until you get up to a high enough temperature. And then it will start with its symharmonic oscillation. And then you have these vibrational energy states. And so when you look at that IR spectrum, depending on the temperature of your molecule, you might see just one of these, or you might see both of them together. And so if you have two patterns, which right, you have spacings that aren't exactly equal, like you have spacing like this, and then you have another one that's just a little bit off. It's been a long time. It's been 17 years since I looked at IR spectroscopy, but that's because you have both the vibrational and the rotational at play. And so in first semester physics, when we talked about the molar specific heats of an ideal gas, we had the molar specific heat of a monatomic ideal gas was very simple. It was 3/2 R. And if it was diatomic at really low temperatures, it was still 3/2 R, because all of your energy is just going into 3 translational degrees of freedom. But then if you got up into a mid-level, it went to 5/2. 5/2 because we're adding, I think it was rotation that comes in first, so adding 2 degrees of freedom for rotation. And then we got even higher and we added 2 more, so it goes to 7/2 R because we're adding in the vibrational. And like I said, I might have the vibrational energy and the rotational. Okay, so that is a $100 stylus. I need to be careful with it. Like a month after I got it, I dropped it like this and splintered the tip. Fortunately, tips are cheap to replace. You need to be careful. So these are things that you use in chemistry that come from quantum mechanics. They're not the hydrogen atom, which is what our focus has been. But I think it's important to have some understanding of these as well, so that you can see, yeah, all of this stuff is fairly fundamental. In physics class today, when I was, it's sad, I'm sure, for Chad, because I keep referring to him. Chad knows this, Chad knows that. Chad knows that while general and college physics seem really, really hard for a freshman level class, compared to an upper level physics class, they're not so hard.
It's not hard to plug in numbers to
Don't say that to your classmates. They will not find it pleasant. But these connections of how it's useful, that's what we want you to come out of here with. Are you going to be able to reproduce all of the quantum physics calculations? I doubt it. By the time school starts next year, you'll be lucky to pull a few out. But you'll have the knowledge of how it fits together, and so you can go back and look at something, refresh, and say, yeah, that's how it works.
So going back to the low temperature
Mm-hmm.
deal, like, how is it possible that these molecules have a quantized energy and it can't be 0 for vibrational energy, and yet it doesn't have enough energy at low temperatures?
Yeah, it doesn't have enough energy to, see, I probably should have spent more time looking at that just to make sure I'm right on it. Because, what we always say, it doesn't have enough energy to make it oscillate. And so it's behaving like it's rigid.
Okay. So there has to be an external energy applied in order for it to have those quantized energy levels?
That's my recollection. Like I said, I can be wrong because I didn't go and carefully look at it before class.
Okay. Because if they're not rigid, then they do have some potential energy, right, between them?
That's right.
Okay.
And actually, it probably is rotation that comes first. That's why this problem is rotation without vibration.
I think that's what I remember. We did a lab like this in thermal last semester. Heat capacities.
You did heat capacities with the gas and raising the temperature?
Just monatomic, diatomic, triatomic, and looking at their the tube. We used the Kunz tube. Have you heard of that?
The Kunz tube is a tube that you send waves down and it has resonance.
Right, we use the resonance to find their heat capacities. Don't ask me how we did that. Remember we listened to the...
It was a very
No.
Well, with Kunz tube, what you find is the speed of the sound wave in the material fundamentally. And so, yeah, must have been relating the molar specific heat to it. Okay, so that problem, I took a few pages and I took half our class period, but fundamentally it wasn't a hard problem. It was a different problem that you would have to think your way through it because you haven't done anything like it, right? But the first step, find the Hamiltonian. Once you isolate what kind of energy it can have, it kind of writes itself. You had to do that thinking of what kind of energy it can have. And then from there, the next step was realizing, hey, we already have the eigenstates for that Hamiltonian. Right? It would have been a whole lot less fun if we didn't already have the eigenstates and the eigenvalues for the Hamiltonian.
Would we have had to use matrix math to get there? Or?
No, you would have had to essentially reinvent the same thing we did when we found the solution to the radial equation, or the Schrodinger equation, or the radial aspect of it. Yeah, which we don't want to do. You've seen it done. You know there's a way. Actually, you've seen some of the steps and you've been told these are the solutions that fit this equation. Yeah, some genius. Okay. Is there another problem that you have questions about?
Just work through the rest of it because you kind of talked about it a little bit. But
Okay. So so number 4. Right, come on.
I think the 2 was too easy. It was 40 points. Did it 3 points.
Okay. It will write on this page. It will not write on this page. Why won't it write on this page? I have no clue. But it writes on this page fine. I think it's writing in visible ink. Well, let's try adding more pages and see if it'll write on new pages. Good. It wrote on my new page, so let's do it. So we're trying to find L, M1, Lx, L, M2. I'm going to erase the commas here because it makes it look like it's L1. And likewise, we're trying to find for Ly. So we start with what we've already done. L plus L minus equals 2Lx. So Lx equals L plus L minus over 2. And we worked all that out before, right? So that means I'm going to have factor out the 1/2 everywhere. So I'm going to have that. And then we have that right, because it's going to raise M2 by 1, then I have to have M1 equals M2 plus 1. And then that's multiplied by, and I'm just going to put a plus of M2. We'll look up what that is because I didn't bring my textbook in. Actually, I suppose I brought the solution. I can look there because I have to have it in my solution. So but what if I don't want to? Well, I mean, it's an option for me. It's for you. That's not an option, right? Okay, so that's what the A plus is. And then if I do the other one, now it's M2 minus 1 because we have the lowering operator, where A minus of M2 is equal to only difference is that last sign was a minus instead of a plus. And so I suppose if I was turning this in, I would go ahead and write this out by putting in the A plus where I have A plus written and the A minus where I have A minus written. But this is all the information you need. You now just have so I'm doing it. Whoa. Hey, look, now it's taking writing apparently on that page. Also move forward, I don't know how many pages. Sometimes I confuse myself. So there's the answer for LX. And I won't do the LY. The LY is only different by changing a plus sign to a minus sign and putting an I in there. Because the LY operator was L plus minus, L minus is equal to 2I LY. So since we found independently what the L plus and the L minus are, it's pretty easy to piece together the LY once we've done that. Any difficulties in the understanding part?
Can you say this part about the LY again?
Well, the LY operate. Okay, so things that are important. We found this with that, right? And likewise, we found this with that. And so since my LX was the first green box plus the second green box, that's what I wrote for my answer. Now, if I did the LY, I have that relationship. So LY is equal to 1 over 2I times L plus L. And I did that in class too. Put a minus sign where I meant to. What did I just do? Well, so my LY, what's different is that there is an I here and it's a minus instead of a plus there. That's the only difference. Any other homework that you have questions about? Number 5. Yeah, I can do number 5.
I feel like number 2, I understood it, and then when I did it, it seemed too easier. It seemed like for 40 points, it should have taken more work.
It's not super complicated. Mine looks super complicated. Mine takes, let's see, where's the 2? Page 4, 5. Yeah. Mine takes this much space, but half of that is showing that I didn't have to worry about A being the board radius being different for a helium atom as it is for a tritium.
Okay.
That was half of my work.
Do you end up with like a decimal answer in the end?
What? Yes. In fact, can you tell me what yours are? I'll verify.
0.702.
0.702 is the probability of, yes.
Oh, okay.
Probability of staying in the ground state is 0.702. It's a good sign that you did it right.
I guess.
Either that or your random number generator was really on. Well, that's what I prepared today. I want to make sure that we don't have this angst about the homework.
I appreciate it.
All right, so if you don't have questions, we'll end early. Because that's all I'm prepared to talk about today.
How many more lectures do we have for the hydrogen atom? Because I know it's just a review the last 4 classes.
Yes. So in theory, that would be one more before we start reviewing. I may cut some review to get a little more in on the spin because, you have to have the last quantum number to understand the things here because it gets complicated. Things like, singlet state versus triplet state, those are things that it's good to have an understanding of instead of like, well, I know they exist.
Yeah. Okay.